Okay, so we're going to talk about polynomial functions, and we're going to talk a little more about the domain and range that we started last time. And we're going to introduce a new notation here, interval notation. So last time we talked about set notation. Today we're going to learn another one quite close to it. It's called interval notation. Polynomial functions and also domain and range. So we did talk about polynomials. We talked about functions today. Now we're going to combine both of them, see what polynomial functions are. So remember, a polynomial is something like, let's say, x to the third plus 2x minus 1, right? Again, a polynomial doesn't have these kind of terms. There's no negative power. There's no variables in the denominator. Also, there's no radical or, let's say, a fraction as a power. Okay, this is what a polynomial is, basically. So when you take a polynomial and you give it a name, function notation.
Those are the exceptions of polynomials, no?
Yes, so polynomial does not have, so without. Okay, so when you take a polynomial, then you add a name to it, function notation as we saw last time, and that becomes a polynomial function. So this is a polynomial function. So this, again, this is the name of the function. It could be any letter. This is, of course, is the variable. And this is basically the expression of the polynomial. So that's what a polynomial function is. They're very similar. Whatever we do with polynomials, whatever we did before, we do with these. We can add them, subtract, multiply, divide, and everything else. So last time we saw how to graph two functions, two types of functions. So we did the first linear functions. How does a graph of a linear function look like?
It's a straight line.
That's right, it's a straight line. That's why it's called linear. For example, f of x is x minus plus 2 or something like that. So the power is 1, so this makes it linear. And the graph is always a straight line. And when we did to graph it, we filled up a table with some values. For example, here, if we take 1, let's say -2 and 0. If you plug 1 here, you get 3. If you plug -2, it will be -2 plus 2 will be 0. If you plug 0, you get 2. Or you can plug any number you want. We took a few, but technically we can take any real number. What did we call again this column? What did we call this column last time?
Domain and range.
That's right. This is a domain. And this one here is the range. Again, here, usually pick some convenient integers. We don't want to pick any decimals or fractions because these are easier to deal with. These integers here are easier. But practically, you can take any real number. So the domain is basically, domain is any real number. And we know what real numbers are. Basically, every number you can think of except complex numbers. So decimals, negatives, positives, fractions, radicals, rational, irrational. So you can plug any one of these here, and you will for sure have a value of y here. If you look at the number line, when we represent the numbers, we say 0 here, infinity. So the numbers go up, 1, 2, 3, 4, all the way to infinity. You don't stop. On the other side, -1, -2, and so on, all the way to negative infinity. So the domain is all these numbers, all the real numbers, which we can write in interval notation like this. So we say domain, that's the name of the set, then colon, and we just say between these, from negative infinity all the way to positive infinity. And last time we used curly braces, but today for interval notation, we don't use curly braces. We don't use these. Instead, we use either parentheses or brackets, not these. For infinities, we always use parentheses around them. And brackets, we're going to see where or when we need to use brackets over these in the next few problems. So this is, again, interval notation. It just means from one value to the other. We don't have to list all the values as we did last time with set notation. For example, we had a set, we did this, and we list all the values, however many we have, we list all of them and we close. This is set notation. But interval notation, we don't list all of them. We just list the first and the last one. The lowest and the highest, in this case, negative infinity to positive infinity.
So you're saying that, for example, when we have 1,3 in like the table, that would be an interval notation?
That's right. So we just pick the lowest and the highest. Usually when we have too many values to list, for example here, all the numbers pretty much, an infinitely many number of numbers, we can't list all of them in set notation. We just say, oh, it just goes between this and this. So this is what we mean by interval notation, because the line extends in both directions. We can take any value of x, we're gonna get some value of y. So any number from here, any real number, we can plug here and get some y. Same thing with the y, as you can see, each number here, or each point has a y. For example, this point here has this y, this here, and as this goes up or this goes down, there's always gonna be a y coordinate for each point. So also the range.
I guess what I'm getting confused is how do you, for example, differentiate the interval notation from a point in?
Okay, I'll explain everything. Okay, we're just getting started. There's a lot more information coming up. So the interval notation, again, the domain is the values of x. We can plug anything, and the range is also any number. So any number you plug from here, you get some y back. Usually we get these for graphs, because graphs don't stop. Most of the time they're limited, or they extend infinitely in both directions or one direction, or they could even be limited, but they have so many points. So basically a graph is so many tiny points if you count all the decimals. For example, you take this, take a graph like this. Let's say this graph goes from here all the way to here. And this is probably, let's say, -5, maybe 4 here. So that's another graph. The only difference is this graph does not extend. It's only this piece exactly. Unlike this one for a line, it keeps going infinitely in both directions. That's why the domain is all the real numbers, basically any number from negative infinity to positive infinity. But for this graph, this is the x-axis. This is the y-axis. So now, for this specific graph, what is the interval, or in other words, the domain or the values of x? They go between what values? Domain is the value of x.
5 and 4.
That's right. The x goes from here to here, because this is the highest point here, the lowest point is this. So all the x values basically range between -5 and 4. So instead of writing all the values, just going to say this. Goes between this and this. If you are going to list all of them, we have so many here. Not only the integers, think about the decimals, 0.1, 0.2, 0.3, and so on. There are so many points to list in set notation, so we can't list all of them. Instead, we're just going to say, well, they just go between -5 and 4. That's the domain. But we need to wrap them around with something, either parentheses or brackets. So here's how you choose what to use, whether brackets or parentheses. So if you look over here, this graph is, the end of this graph is shaded, okay? It's not an arrow, so it stops right here, it's shaded. That means that's included in the graph. This point is included in the graph. So if it's included, we use brackets, not parentheses. This point itself, -5, is included, so we're going to use a bracket. But if you look at the other side of the graph, you have a hole in the graph, this means that the 4 here is not included. So basically this point is skipped. There's a hole in the graph, we skip it. So to say that in the interval notation, we use this. We use parentheses. So this means the -5 is included because in the graph it's continuous. And this means the 4 is not included because we have a hole in the graph. So this point, we cannot plug it. So say you were doing a table, you can plug any value from -4, -5, -5 itself, all the way to 4, but not including the 4. You will not be able to plug the 4 here because it's not recognized. It's not part of this graph. Only all the other points below 5 and below 4 and all the way to -5. So
Oh, that's weird.
brackets,
Why?
brackets are used for when the graph is continuous or shaded. If you don't see a hole in it, that means the point is included. Okay.
So why if your domain, it's in the infinite, it's parentheses in your range?
For infinities, always use that because the infinity itself, the number we don't know. There is no, I mean, infinity is just a symbol, but we don't know that number itself. In other words, the numbers never end. There's no end into this. So remember with infinities, we're always going to use parentheses. So if the point is included, use brackets. And if the point is not included, if you see a hole in the graph, use these parentheses. If you see a hole like this, that means not included or excluded. Okay, so that's convenient with graphs because graphs can have many values. So instead of writing all the values, we just need 2 values, the lowest and the highest. And sometimes the graph stops. If it stops, we use one of these symbols. If it does not stop, if you see an arrow, that means it keeps going. For example, here it goes down here to -infinity, it never stops. Here it keeps going up and up to +infinity. That's why we said the domain and range for linear functions is pretty much any number. But some graphs are limited, for example, this one. It's only between this and this. So that's the domain. What about the range, by the way? If you look at the graph, this is the y-axis. So what is the range?
The y.
The y, and from the graph, it goes between what and what? If we put some numbers here, let me give you some values, maybe this here. This probably, let's say -3. Goes all the way up here. Let's say this is probably 6. All right, so the y-axis, we have the graph. So the y's of this graph, they are between what values? What's the interval?
Brackets -3, comma 6, parentheses.
That's right. All the y values for this graph basically go from here, -3, all the way to 6. There's nothing beyond here, nothing beyond here. So all our values, basically, if you do a table, all your y values will be numbers between -3 and 6. And x values will be between -5 and 4, not including the 4. And also here, not including the 6. So it is a limited table. So the range goes from here to here, -3, all the way to 6. And again, this is included, as you can see. If it's included, we use a bracket around the number. However, the 6 here, because if you don't have x, you can't have y. So 4 is not included. Therefore, there is no y corresponding to it because you gotta have an x in order to have a y. So if you don't have an x, you can't have the y here. So 6 is not included because you have a hole in the graph. So I'm gonna use this symbol to exclude it. So that's pretty much how you read the domain and range from a graph. You just read 2 values, the lowest and the highest, and that's it. You don't have to list all of them.
But whenever they give us this graph, it's gonna look like this, right? One end shaded, one end not shaded, if that's what they're asking about. Because I'm in my head, I'm trying to figure out, well, if the points are on the graph and we're talking about it, why is it not included? It doesn't make sense about the not included part. I mean, I understand how to write it and all those things. It's just not included. I'm like, okay.
It depends on the function and the numbers that can be solved for the function?
So this graph will be given to you. These graphs, I'll give you a graph like this. But for the common functions, for example, linear and quadratic and third degree, those we talked about. We're going to talk about them again. They have specific domains based on the shape of the graph and how it extends either in both directions or one direction. But this is just a graph, random graph that I made up. It doesn't have a specific function. Maybe it does, but I did not think of a function to do it. But with visual functions like linear and quadratic and second degree, each one has its own domain and range. So from now on, just remember, for the linear functions, the line extends in both directions. The domain and range are always this for any linear function, as long as it's linear.
So we're not putting real numbers that, well, when I say real numbers, we're not putting like 1, 2, 3, 4. We're just putting negative infinity to positive infinity with the parentheses.
That's right. So basically the values here that you can choose for a table are included here, but we don't know what infinity and positive infinity themselves are, but we can take any numbers in between. You can choose, let's say you want to graph this. I didn't give you a table. You can make up your own table with any values you want, any real numbers. So the domain for linear functions, you're free to choose any number, and the range, as you can see, both x and y extend in both directions. This is the x-axis, the y-axis. We're going to talk about the second degree functions also, second degree and third degree, and see how the domain or the range behave based on the function or based on the graph. So from now on, you don't need to see the graph of a linear function. So if it's linear, that means it's a line that extends in both directions infinitely. So you can immediately write this as an answer. If you're asked what's the domain, you would say, oh, it's a linear function. The domain's got to be this, and the range is got to be this as well. Some common functions we will learn, and you can say right away based on the graph or the examples that we were doing, so we can say it right away. Let's look at another one. Let's look at another example like this before we do the quadratic, maybe even third degree, so x and y. So let's say I have maybe this graph goes, it goes from here, for example, all the way here, and so is the graph. He has a hole at this end. He has an arrow on the other end. So what is the domain of this, and what is the range? The domains, again, are the values of x. For this graph, the values of x go between what values exactly?
Parenthesis minus 3 comma infinitive parenthesis.
That's right. All the x values for this graph, they start from here, -3. And it does not stop here. What does that mean? Where does it go?
Keeps going forever.
Infinity.
Forever, that's right, infinity. So infinity. That's it. That's all you have to do. So any number, any point here will be in this interval. So interval is basically, it's like a space or a limited range of values. So we know for a fact it goes between this and this. For example, if you talk about the age of
The parentheses.
That's right. That's right. Negative is not included, so we use that. And for this, for infinities, we always use parentheses as well. So even if you didn't see the graph, let's say you don't see this, ignore this. Can you tell that is -3 included or not based on this interval?
Not
What tells you that it's not included?
the parenthesis.
Exactly. The parentheses make it not included. Let's say you want to talk about, for example, the age of voting. So in an interval, what is the age of voting in an interval?
18 to whatever.
That's right. 18 to whatever. That's right. To the highest number possible.
Oh, in the United States, you guys vote at 18, but legal age for drinking is 21?
Yeah.
Oh, I thought it was the same, everything 21. Interesting.
No. They want you as early as possible.
You can also join the military at 16 and carry a gun and kill people at 16.
Yep.
Okay, that's how twisted politics are. Anyway, so 18 all the way, let's say maybe the oldest human could be whatever, 150. What about 18? Is it valid? Is it included or not?
Yes.
Can you
Yeah.
vote on 18? Yes. So do we use brackets or parentheses?
Bracket.
Bracket.
A
Bracket,
bracket.
because that 18 itself is good. But if I put 17 here, what would I have to change?
You would have to put parentheses.
Parentheses.
You have to put
Right.
a parentheses.
If I put 17 here, so that's not an eligible age to vote. So I'm going to exclude the 17. I'm going to say this, but you got to be 17 and up.
So basically, anything after.
Okay, so that's the difference between parentheses here and the brackets. What about the range of this same graph? Let's say this.
Well, it depends where is y.
1 second. You put the 150. What would you have put after it? In the top example, you would have put
Let's say, assuming this is the highest age, so this will be included.
Okay.
This is just a random example. I'll include this because you want whatever highest age is, you want them to vote.
So 17 would be parentheses, and the 150 on the end would be a bracket still.
That's right. So excluding the 17-year-olds.
So it's if the 17 is 18 and up.
Mm-hmm. That's right. What is the range here? For the values of y for the graph. What is the lowest?
1 infinite.
1.
Right. The lowest y is here, which is 1, and it does not stop. Since this one does not stop, it keeps going up. So it might be net 1 here, then probably 2 here, 3, 4, and 5. So this does not stop. The y also does not stop. Since it's going up, so it's going towards infinity. Unless the graph was going, let's say it was going down, this way, then it will be going to negative infinity. But this one is positive infinity. So the range is 1 to infinity. What we use around 1 again? It is not included, as you can see here. Okay, so if x doesn't exist, then -3. Therefore, this one doesn't exist also, because we have to have an x to have a y. Okay, that's very simple to read domain and range from graphs. No big deal, just look at the numbers. If you see an arrow, it means it goes to infinity. Could be this way going to positive infinity. If the graph was facing the other way, this way, it would be negative infinity. And this means included, the whole means not included. That is pretty much how you read the domain and range from a graph. Let's go back to our common functions. So again, for linear functions, it's always going to be this, both domain and range. You don't even have to do the graph or a table. So this is a fact. What about quadratic functions?
Mm.
That's what we did last time. What is a quadratic function again? How does the graph look like?
Parabola.
Parabola, that's right. And we, as we saw last time, it's either facing up or down. Let's say maybe this way, probably this way. X-axis, this is the y-axis. Parabola does not stop again because just because we choose, 5 values of x last time, doesn't mean that's all there is to the domain. We could choose any real number. As you can see, the graph extends here and here. Basically, x goes up here to positive infinity. And in this direction, -1, -2, -3, -4, and so on. So it goes to negative infinity. So for quadratic functions, for example, f of x, let's say x to the second minus 3. This is not exactly the graph of it, but we can make it the graph of it if we make this positive 1. Okay, so if this is 1, so this one matches this one now, and the domain again for quadratic functions is always all the numbers. You can pick any numbers you want, you plug them and you get the y, as we did last time. So the domain is all of that. What about the range? Is it always the same?
No,
That's right. Why?
because the curve of the parabola is hitting number 1.
That's right. So this could be here, could be here,
So you would have to do,
could be anywhere. That's right. So it depends on the graph itself, depending on the function. For this specific one, the y starts from where to where? The range. So this is the y-axis.
1.
1 to
That's right.
infinity.
So the lowest point here in this graph is here. The lowest point is here. So there's no y below the 1. So all the y's are here and up. So 1 is here, for example, about 2 here, about 3, 4, and 5, and so on. So it doesn't stop. The graph doesn't stop. So it goes from 1 to
Infinity.
That's right, goes from 1 to infinity. And what do I use around 1? Is it a bracket or a parenthesis?
A bracket.
That's right. As long as you don't see a hole here, the graph is continuous. Every point is included here, basically. Unless you see a hole here, then you'd use parentheses, but it's continuous. It's continuous and it's included, so we're going to use a bracket. As always, what do we use around infinity?
Parentheses.
Parentheses. Okay, so that's all here. So the question will say, write the domain and range in interval notation. Okay, so this is again what we call interval notation. You just need the lowest and the highest. You don't have to list all the numbers. We have 2 minutes to list. You just write the lowest and the highest. Okay, so for quadratic functions, the graph always looks like this. It may be facing down, like we said last time. If it faces down, then, for example, if the graph was going like this, down, so it starts from 1 to negative infinity. Or you would put in negative infinity on the left side. So negative infinity to 1 if it was facing down. If it faces up, 1 to positive infinity. But the domain will always be this. So remember this, for quadratic functions, you don't have to graph it, you don't have to look at the graph. You can immediately tell that the domain is negative infinity to positive infinity. We know why, because the graph extends in both directions, whether it's facing upwards or downwards. There's no limit to the x, to the x, so the x extends in both directions. But the y is wherever the graph starts from. So we call this the lowest point of the graph. We call this the vertex. That lowest point here is called the vertex. Okay, the vertex here is 1, or x0, and y1. Basically, this point here is the lowest point of the graph, is the vertex. Or if the graph is like this will be the vertex.
So you said the vertex is what, sorry?
The lowest point of the graph, or the highest one if the graph is going downwards like that.
So you only have a vertex in quadratic functions.
That's right. This U-shaped graph parabolas, yes, we have a vertex in it.
So it doesn't apply to any of the other graphs?
Not exactly. So it depends on the graph of the function. There are other functions, but we're not going to go over them in this class that might have a vertex. But for now, just remember, first degree is a straight line. Second degree is a U-shaped, and it has a vertex. And we're also going to see third degree, the common functions, third degree functions or cubic functions, whatever they might be called. You can graph any functions you want, just like we did last time. Just make a table, plug as many x's as possible, get some y's, and put those in a graph, and you'll see the shape of the graph. So third degree. Okay, so at least remember these basic ones. Remember the shape of their graphs, the domain, and how to find the range. If it's not immediately available from the graph. So third degree is, let's say, the highest power is 3, maybe plus something or minus something. So that's a third degree function. I'll give you the graph right away. You guys can, if you want, you can later do it yourself. Play with the numbers and you'll see it. It looks like this. Goes a little close like that, and not exactly that. Something like that. Third degree functions have the graph like this. The graph, depending on the numbers, you may have +2 here, or you may have 3 here. So the graph could be shifted left, right, up, down, it depends. But for this specific one, it goes through the center of the graph.
So just do 0.0.
Again?
You said it goes through the center of the graph, so it's gonna hit the 0 on
That's
both.
right. That's right. If you plug 0 here, if you plug 0 in the function, you get 0. If you plug 0 here, you get 0. So both, so x and y are 0 here, because f of 0 is 0. Now, what is the domain? Just by looking at the graph, what do you think the domain is?
Well, it depends. Does these lines kind of open up as they go, or do they keep going up in a straight line?
I think the infinity, negative and positive.
Infinity. It doesn't matter if it opens up or that. You see that the graph goes in both directions. It doesn't stop in both directions, okay? So the domain basically is any number.
I know, but it wouldn't matter if it stay in a straight line for
Not
X.
really. As long as it goes up, even if it's a straight line, even if it's a linear function, the fact that the line extends in both directions, the domain and range are any number, negative infinity to
No,
positive.
no, no. I don't mean a straight line that way. I mean a straight line vertically.
For this function, the graph is like this. So it goes down this way, keeps going down to infinity. It goes up here to infinity. It does not stop. That's all.
I know, but in X, does it stay vertically, or does it like up and up to the side? You know what I mean? Because here it looks like.
It wouldn't matter if we went this way, or went that way, or went that way. As long as it has an arrow, that means it does not stop. So that's all that matters, okay? So the domain is negative infinity to positive infinity. For the range, it's the same thing. So this is just like a straight line. They behave the same way. The domain and range both extend in both directions infinitely. So for that, negative infinity. So these kind of save you time to answer questions. So you don't have to graph, you don't have to do a table. If I give you a function like this and say, write the domain in interval notation, you can write it right away. Same thing with the range. You don't have to graph it, unless I said graph this function and then get the domain and range. So most of the time you can answer these immediately in 2 seconds. Same thing with this. So for linear, remember, the domain and range is always this. For quadratic, the domain is always this, but this one depends. Depends on the graph itself. Okay, this one is not always the same. Again, this could be up, could be down, right, left, but this will always be the same. So if I give you a quadratic function and it says write the domain in interval notation, you can write this immediately. Don't worry about the graph. You don't have to graph it. Unless I say graph it first, then you would grab it and look at the domain and range from the graph. Or it may give you just a graph like this, and it will ask you to read the x, the domain and the range from the graph itself. So you'll be given a graph with numbers on it. You'll see the numbers, you'll see everything. You just use the appropriate symbols to get the appropriate numbers from that graph. Okay, so that's the domain and range in interval notation. Do not confuse this with set notation, which we learned last time. Okay, so remember, at least with these basic functions, linear, quadratic, and third degree, they are always like this. And you can graph any function. If you don't know the shape of any function, you can feel free to do a table, choose a few values, find the y, put the points in a graph, whatever it might be, and then you'll see your shape of whatever function you're working with. But at least remember this sketch for third degree closely, something like this. Quadratic's always a U, up or down, parabola. Linear, of course, is a straight line. Okay, everybody, any questions? Any questions, everyone, before we move on to the next thing? And again, in the previous lecture, we learned how to graph this, graph the linear functions. You can graph any function the same way. But at least, like I said, remember the shape of at least these basic ones, first, second, and third degree. Next thing we're going to do is talk a little bit more about polynomial functions. So something like this. You'll see that we can add these, we can multiply them, we can divide. Whatever we do with polynomials, we can do with functions, because technically, a polynomial function is just basically a polynomial. So let's do that as number 2, because this was number 1. So domain and range. We can do operations now with polynomial functions. Okay, so you need 2 or more polynomial functions. Let's say 3x minus 1, and some other polynomial, for example, g of x, equals some other stuff, let's say 7x plus 4. So you can do a bunch of things with these two. You can add them, subtract, multiply, even divide. Let's see how to add. So let's say this is how the notation is, like f plus g of x, f plus g of x. What this means is simply add f and g. You take f of x, and you add it to g of x. Okay, what is f of x equal to? What is f of x? From what given?
3x minus 1.
That's right.
3x.
3x minus 1
3x minus 1.
plus,
7x plus 4.
that's right, g of x, which is 7x plus 4. That's all there is to it. So don't let this notation confuse you. It just means add the 2. You don't even have to write this step. You can
Is
just
that a 7 or 2?
7. This one 7. Okay, so just add the 2. So you get
10x plus
10x
3.
plus 3. Okay, so that's what the notation is for. It just means add. It could be a subtraction here. It could be any other operation. Basically, take your 2 polynomials, 2 expressions, and do that operation with them. You may also say subtract, just like subtracting polynomials. So let's say g minus f. Okay, g minus f of x. So this does not mean times x. It just means of x, meaning these two both have x in them. As you can see, they both have the same variable x. So again, take g of x minus f of x.
But here they would tell you what you're subtracting from, right?
It did. It says you're
In this
taking.
case, it's not a word, it's in the same order here. So there's no word problem here. Just do the same order, g minus f. Okay, unless there was a word problem, subtract this from this, then that's when you figure out the order. But here it's all this set up for you. Just write g, which is 7x plus 4. Then the minus, it's important that you put the second one in parentheses. Whichever one comes second, just like we saw with polynomials, this has to be in parentheses, not necessarily the first one. So negative or minus f. So f is this one, has to be in parentheses. And after that, you simplify. So what do you do first here to simplify this?
You distribute the sign, the negative sign.
All right, I'm going to distribute this first. 7x plus 4 minus 3x plus 1. So this would be
Combine those like.
X plus 5.
okay. So that's the difference of these two functions. Difference, and this is the sum. Okay, when you add two things, you get the sum. This is difference. Could be a multiplication. It could be anything. Let's do the multiplication now. Same thing. So you may say f g like this. Fg, or you may see a little dot in between, which means the same thing, f times g. Again, this does not mean times x, it just means of x, okay? F times g of x. This is meaningless. It doesn't mean you have to add x at the end. You see here, I did not add this one at the end of this. I just wrote g and f. Same thing here, we're gonna write f, which is 3x minus 1. Put that in parentheses, and then we have this multiplication, so times the other one. Or before that, let me write the functions notation first. So it's got to be f of x times g of x. That's what this means. Write the f and in parentheses times g. Okay, so that's f multiply. And you distribute, okay? You distribute this.
21x squared.
That's right. That's 7 times 7, that's 21. x1 times x1 is x2. And
12x
3x, right, plus 12x.
minus 7x
Minus 7x,
minus 4.
right, minus 4. Combine any like terms. What do we combine?
21x plus 5x,
That would be
I mean plus 5x
okay.
minus 4.
Minus 4. Okay, that's all the operations. There is division, but we're going to do it in the future with polynomials. We have to do polynomials first, and then we'll do it with. Or if you see it, you just put one over the other. If it says f divide g, just put f over g. It will be a fraction, f over g. So all the operations, like I said, that we did with the algebraic expressions or with the polynomials apply to polynomial functions. These are just names. We basically given names to polynomials. Each polynomial has a lot of name, but the operations are pretty much the same. Okay, everybody, you guys all right? Any questions before I move on to another section?
Are you still doing the tutoring for Learning Center?
Yeah. We'll talk about it after class, or email me, okay?
Professor, I'll send you a private message whenever you get a chance, please.
Right. If you guys have any questions about tutoring, email me later and I'll get back to you. So now let's see another thing, evaluation of these functions.
What about division?
Yeah, like I said, we'll do that in the future. When we do factoring. But for now, if you see division, I don't know if it's in the homework, probably not. It's f divided by g, just put f over g. For example, 3x minus 1 over 7x plus 4. Just put it like that. That's all you have to do. If you need to plug a number into that, then plug it in x and x, just in case you see it. But in the future, we're going to learn how to do that in detail. Evaluating, let's say, polynomial functions. Sometimes, let's say f plus g. Let's take a couple of functions here. F, second minus 1, and g, maybe 2x plus 3. Sometimes you may see something like this, f plus g, but not x here, as we saw before, but a specific number, for example, 1. Unlike here, you see you have x, you have x, you have x. You may have a specific number here, f plus g of 1. So what do you think that is?
You plug the 1 into the x.
Mm-hmm. That's right. So this means we're going to plug the 1 into both of these and add the result. So it's going to be basically 1 plugs into f, 1 plugs into g. So basically going to f of 1 plus g of 1, because we have a specific number. If you have x and x, you could just add the two expressions. But if you have a specific value, then now we're going to plug that value here into f, also here into g. So 1 into f, this is f. We're going to plug 1 here. It will be 1 to the second minus 1. Then plus, this time we're going to plug 1 into g. 1 into g, that's g. We're going to plug 1 here into the x, and also here. So it'll be 2 times 1 plus 3. Okay, that's all you have to do. Plug 1 into both. And whatever operation you have, could be addition here, subtraction, multiplication, or even division. Just simplify and add. So let's simplify this expression using PEMDAS. 1 to the second is 1, minus 1 plus 2 times 1 is 2 plus 3. This cancels, so this will be 5. That's the answer to this one. F plus g of 1 is basically 5. Or it might be, let's say, multiplication. Fg of maybe some other number, let's say negative 2. Okay, f times g of negative 2. What does that mean again?
Plug in the -2 where the x is.
That's right. So it's f of negative 2 multiply g of negative 2. Okay, so the negative 2 goes into both while keeping this multiplication. How do you find f of negative 2?
My brain hurts from this fucking algebra.
Okay, how do you find f of negative 2?
Okay, -2 to the second.
Squared minus 1.
Okay,
That's
so let's plug negative 2 into f, right? This is f. I'm going to plug negative 2 here and here, so negative 2 to the second minus 1. Multiply, so we have a multiplication here, and g of negative 2. So negative 2 into g, that's g, so we're going to plug negative 2 here and here.
times 2 plus
That's
2.
right. To make things clear, you may want to put these in brackets, this whole thing in brackets, and this whole thing in bracket as well. That way you can clearly separate them. So put this here. You can do each one separately first.
Is it okay also if you put like double parentheses?
That's okay. You already have parentheses here. We use brackets outside, but it's okay. It might be a little confusing to put parentheses after parentheses. The brackets kind of tells you where it starts and where it ends.
I know, but
Okay, so what is negative 2 to the second?
4.
4 minus 1 would be 3.
3.
And here we have
-4 plus 3.
which is negative 1.
1.
And finally, this is negative 3. Okay, so that's what it means. Just keep that operation, whatever it might be. Evaluate the two functions with the number given, and either subtract, add, or multiply. Let's do one with division, just in case you see a division in the homework. Let's say f over g of, let's say, 3. How do you do that?
So 3 to the second minus 1.
Break it down first like this. Let's break it down first. So what do I write here now?
F parentheses 3 over G parentheses 3. I mean, yeah.
Like this. Yep, so basically just write whatever functions with the appropriate or with the given operation. Division here, multiplication, addition. Of course, now evaluate. Plug 3 into f. What is f again? That's this is f, so we're going to plug 3 here. So 3 to the second. Minus 1 over g of 3. So 3 into g, that's g. So 2, 3, plus 3. Okay, we plugged it in this function g. Simplify, so that's 9 minus 1 over 6 plus 3, that's 8 over 9. Okay, so these are just some basic notations here. So when you see them in the homework, they just mean basically this. If you have a value here, if you have a number, that means you need to plug it. If this is x, then you just have to combine the two functions, combine this and this, either add or multiply or divide. If you see an x here, so if you see a value, it means you have to plug the value. But if it's x, as you can see, write the two functions together and do the operation that's that the question is asking you to. And that's your polynomial functions. They're not bad, they're just basically polynomials. Okay, everybody, you guys got that? Any questions? Again, it is highly recommended that you rewatch this, okay? The more you watch it, the more sense it will make. Take notes, you know, practice and let me know if you have any issues, okay? Every class, you know, before we start, let me know if you have any questions.